You're in the exam hall. The clock is ticking down. You read a physics question, you write down an answer that makes perfect, logical sense to you in your head, but when results day comes around, the examiner has given you 0 marks for it. Why? Well, zero pleasantries today. We are jumping right into the high-stakes reality of the exam room. Let's dive straight into this and pressure test your physics answers to see if they can actually survive the Cambridge mark scheme.
Let's do a live transformation right now. Look at the left side of the screen. We have a painfully average, mark-losing sentence I see all the time from students. The spring gets longer when you pull it. I mean, is it true? Yes. Is it worth marks? Absolutely not. Now, what's really interesting is the right side. Extension is directly proportional to applied load up to the limit of proportionality. Boom! That is an A-grade, terminology-rich answer. It's the exact same concept but delivered in completely different, exam-safe language.
So let's look at Section 1, the high-band framework, upgrading your exam answers.
Look, ordinary rote revision totally fails under the intense pressure of Cambridge exams. Memorizing facts just isn't enough anymore. Examiners aren't merely looking to see if you know the physics, they are actively hunting for how you express it. To survive, you need this 4-step core answering framework. First, you identify the core concept. Second, you pull the exact evidence or data from the question or graph provided. Third, you apply your scientific reasoning to connect the two. And fourth, and honestly, this is where 90% of students completely drop the ball, you package it in strict examiner wording. If you skip step 4 and use casual everyday language, your answers will completely break under the pressure of the test, and you are leaving guaranteed marks on the table.
All right, let's put this into practice. Section 2, pressure testing. Hooke's law in action.
We're going to apply our framework to a classic Cambridge practical, the stretching of a spring. When you face this in paper 6, you aren't just looking at a spring, right? You're looking at variables, apparatus safety, and data reliability. Look closely at this typical experimental dataset. At a load of 1.0 newtons, the extension is 4.0 millimeters. At 2.0, it's 8.0. At 3.0, it's 12.0. The math is beautiful here. We have a perfect multiplier. We have direct proportionality. But watch what happens at 4.0 newtons. The extension suddenly jumps to 18.0 millimeters. The pattern broke. As an elite student, spotting this crucial moment where direct proportionality breaks down has to be your primary objective.
And that breakdown brings us perfectly to a vital concept, the limit of proportionality. This is literally the point beyond which a material's extension is no longer directly proportional to the applied load. I really need you to understand that memorizing and using this exact terminology is a non-negotiable requirement. If you write something like the point where it stretches too much or where the spring gets ruined, the examiner will simply cross it out. You must secure those method marks by speaking their language.
Now, when you take that Hooke's law data and put it on a graph, do not rush. Look at these vital graph skills. Students constantly rush this step and suffer an immediate loss of easy marks. You must label your axes with both quantities and units, like load/newtons. You have to maximize your scale so it covers over 50% of the grid, otherwise it's just too cramped to be accurate. Plot your points clearly with thin crosses, not big, thick dots that hide the true coordinate. Draw a precise line of best fit, and always identify and double-check any anomalous data. Now take a breath, because in just a moment I am going to reveal the one hidden examiner clue that completely shifts how an answer is graded. It is the absolute difference between an average grade and top marks. But first, you need the rest of the framework to ensure that when I show you this clue, it makes total sense. So stick with me, because leaving now means missing the key to unlocking the entire exam.
Let's escalate things. Section 3, escalation, moments and center of gravity.
We are raising the stakes now with a notoriously tricky topic where the traps are much harder to see. Before calculating anything, establish your foundation. Center of gravity is the point through which the entire weight of an object appears to act. You need to establish this foundational concept before you even begin tackling a balancing calculation. Because if you don't know where the weight is acting from, your distances will be entirely wrong right from step 1.
Okay, it's time to challenge you. This is a pause and predict moment. Imagine a 100-gram mass is at the 10-centimeter mark of a 100-centimeter ruler, which is perfectly balanced at the 50-centimeter mark. Where must a 50-gram mass go to restore equilibrium? I want you to mentally lock in an answer right now. Test your ability to calculate distance from the pivot in your head. Do you have a number? Good. Let's see what a typical student does.
Here is a wonderfully flawed student rationale I pulled from a past paper. The student wrote, the 50-gram mass needs to go to the 90-centimeter mark because 100 times 40 equals 50 times 80. This is a high-stakes spot-the-error moment. Read that quote again. The basic multiplication balance is, sure, 4,000 equals 4,000. But is it correct physics? No way. It's a disaster.
Let's bring out the red pen. On the left is the fatal error. They used mass instead of weight, and centimeters instead of standard meters. Moments are calculated using force times distance, not mass times distance. On the right is the examiner's safe method. You take that 100 grams, convert it to 0.1 kilograms, multiply by the gravitational field strength, which is 9.8 newtons per kilogram, to get the weight force, and then multiply by the standard SI unit of 0.4 meters. Exposing this fatal error of ignoring units is exactly how you protect your grade.
So, let's rebuild that ruined calculation using our high-band framework to guarantee absolute mathematical safety moving forward. First, explicitly identify the principle of moments. Clockwise moments equal anti-clockwise moments. Second, always convert your masses into weight in newtons. Third, calculate the precise distance from the pivot, not from the end of the ruler. And finally, state your final answer relative to the ruler's markings, just as the question asked.
Okay. You've got the framework, you know the traps. It's time to finally reveal that open loop. The ultimate examiner clue isn't actually hiding in the physics formulas at all. It is buried right in front of you in the command words of the question.
Here is the critical difference. If a question asks you to describe the graph, you only state what happens based on the data. You say, the line goes up and then curves. But if the command word is explain, and you just say the line curves, you get 0. Explain means you must provide the underlying scientific reasoning. You have to state that the limit of proportionality has been exceeded. Command word awareness dictates the exact structure of your answer. It's literally the single biggest factor in deciding whether you land in the bottom or the top mark band.
Now, we have covered incredible ground today, but this leaves us with a massive unresolved problem. How do you deploy this entire framework when you sit down in the exam hall and are faced with a completely unfamiliar, never-before-seen practical setup, especially in those final frantic days before the exam? Understanding the theory is one thing, but applying it perfectly to a chaotic, curveball practical under time pressure is an entirely different game.
You cannot walk into that exam room hoping for the best. You need a system to deconstruct the unknown. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We provide the exact tactical breakdowns you need to turn the unknown into a checklist.
Will your current revision strategy actually survive contact with a real Cambridge mark scheme, or will it break under the pressure of those command words? Solving that exact problem of the unfamiliar exam paper is what we're doing next. Your mandatory next step is to click into our explainer on the Physics 0625 Last 7 Days Revision Map. We are going to take a whole paragraph of weak revision planning and transform it live into a high-scoring strategy. This is an absolute binge loop necessity for anyone serious about mastering this subject. Do not step into that exam without it. See it in the next explainer.